Folks, as we continue to look at the use of Biot Savart's law to find magnetic field near some current carriers, we come across this question, which is a standard type of one. We have a current carrier somehow of length 2a, I guess you'd call it. And let's say that current travels towards the top of the page. And we want to find magnetic field from this section of wire at point P. Now, we're not saying necessarily that the wire stands on its own and carries current. That's impossible. It's part of a loop of current somehow, but the rest of those parts of the loop we just don't see here. So anyway, we want to find the magnitude and direction of field at point P, and we're going to do it. Well, here's what you're going to get. All right, I'm going to start the setup. If you're playing at home, what I'm going to you'll hear me recommend that you stop and see what you can do on your own, and then I'll show you the full solution. All right, so what we are going to do is say we're going to use Biot Savart that says that there are elements of this magnetic field from elements of current, like this one, that I call an IDL. All right, Biot Savart's law says that an element of a field has this magnitude, mu naught over 4 pi I dl cross r hat over r squared. Now, if we're going to find the whole field, then we integrate all of the field elements. So what we should talk about is what's the direction of the field element from this current element, and then see if we have to make any adjustments to this, what looks like simple statement, to account for any things like components of fields. So what I will do is first use the right-hand rule to look at what the component of the field dB is from that single current element that we've drawn. So to do that, what we need to do is identify vector r that looks like this. That gives us an r hat direction that looks like that. Vector r and the r hat unit vector are not the same thing. Vector r is quite literally the vector that goes from current element to location of interest. R hat is a unit vector that just says that way. Okay, so right-hand rule application of dl cross r hat says fingers in direction of dl. It means fingers upward. It means curl those fingers of your right hand toward r hat direction, and we do that, we get the direction of the field at point P, our location of interest, and that direction is inward. All right, and no matter where you do that, if you took another one here and said there's an IDL going upward, here's an R, and therefore an R hat like that. If we put fingers in direction of IDL upward and curl them towards r hat direction with our right hand, while our right thumb still points into the page. All right, so all the field elements from all these current elements all point into the page, and thus our vector dB, integrating all those means we can really integrate the scalar dBs, the size of each of the dBs, as opposed to some cases like here's a one where we had to look at components of a dB. This is from our last unit where we said we're adding all the dB vectors, but that means analytically we have to only look at components to add. All right, here there are no components. These elemental fields all point into the page, and thus we integrate their scalar magnitudes. Okay, so that means we do as we said to do. We integrate all the stuff above. Now I'm going to write this as mu naught over 4 pi. I'll pull the I out here because I is assumed to be constant. And then when we say, all right, what is the value of dl cross r hat? Well, what we need there is the magnitude of dl times the magnitude of what I'll call r hat perpendicular. Okay? Well, okay, the magnitude of dl we can leave alone. The magnitude of r hat perpendicular, well, we can draw r hat perpendicular. It looks like that, perpendicular to IDL in order for there to be a cross product. If we call this an angle theta, that same angle shows up in there, and thus r hat perp, so this is magnitude dl times magnitude r hat cos theta. Well, you know what the magnitude of r hat is? It's 1. That is part of the nature of a unit vector. It is a direction with magnitude 1. All right, so what this really evaluates to is dl cos theta, and that, what I forgot is to keep, so what this cross product evaluates to is dl cos theta, and I'll keep the r squared, and that's the stuff we have to integrate. All right, theta is a variable, r is a variable, those r's are non-constant. All right, and dl is the thing we're integrating with respect to. And that can be tricky. There's a couple of options here. I mean, number one, dl is really like probably what we call a dy if we're calling this a y direction. Theta is a variable, r is a variable. The way I like to do this is to write everything in terms of theta. All right, I'll give you a hint. You can write y in terms of theta, and thus you can write an expression for dy. You can write r in terms of theta. And well, then we got a cosine theta, so that's good. So what I'm going to recommend you do is stop now, see if you can do this, get all those things in terms of theta, and then get an integral that's really not very hard to evaluate at all. The hard part's the setup. All right, so my recommendation is as follows. Pause, crank away, come on back, and I'll show you the solution. You didn't pause, did you cheater? Pause! Okay, now, as we said, notice we can write y in terms of theta specifically. Now y, look, here's what I'm calling y. The coordinate, the position of that current element IDL. So y can be expressed as big R, oops, not divided by, y can be expressed as big R tan theta. You need to back up a step. You can justify that tan theta is opposite over adjacent, and this dimension along our x-axis we're calling r, how far from the wire we are. With that in mind, we can differentiate both sides of this expression d theta. We can say dy d theta is, well, r is a constant, and d tan theta d theta is secant squared theta. Secant squared is 1 over cosine squared. So this gives us an expression for dy in terms of d theta. It allows us to sort of convert from one set of units to another. Nice thing about d theta is, look over here to your right, oh, we got a theta. Okay, okay. And now r we can also write in terms of theta. I'm going to shrinky dink this. Notice that we can write little r in terms of theta. If we say that little r, well, if we say cos theta is big R over little r, then little r is big R over cos theta. Our expression has a little r squared in it, so if we say squared, 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 okay. All right? Now, we can continue and say that our b, okay, vector sure, is mu naught I over 4 pi. All right, dl is dy. We okay with that? dl is dy. This is our dl, top left in the diagram. That's a dy. So our first, right, this dy in our expression is r over cos squared theta d theta. I'm going to put the d theta out here at the end. All right, now I'm going to keep this cos theta, that goes here. And now I'm going to do this divided by r squared. Well, r squared is r squared over cos squared theta. All right. Yeah, I know r squared is this, but notice we are dividing by r squared up here. So there's our divided by r squared. And look at this. Cos squared, cos squared. Factor of r, factor of r. R is a constant anyway, so look, all we have is b is mu naught I over 4 pi big R, and the only thing we have to integrate is cos theta d theta. All right, and we can say that these angles vary from, well, there's a negative theta down here to a positive theta up here. So there are our limits of integration. And we're going to get that b is mu naught I over 4 pi r sine theta from negative theta to theta. So that's sine theta minus sine of negative theta. Well, sine of, the nature of a sine curve looks like that. So the sine of negative theta is negative sine theta. So what we're doing here is sine theta minus negative sine theta, or 2 sine theta. Okay, so what we get is mu naught I 4 pi r 2 sine theta, which simplifies to what we want, mu naught I over 2 pi r sine theta. Now, oops, to make this a vector equation, because I've carried vector the whole way through, to carry vector, we know that this field is into the page via our little right-hand rule analysis there. Okay? Now, extending to an infinite wire. All right, that was one of the recommendations, extending to an infinite wire. The question is, what are the limits of theta? Well, if this wire gets really, really long, then theta gets, as we're looking way up there to the top of the wire, theta approaches 90 degrees. Sine of theta is 1. So for an infinitely long wire, this thing approaches mu naught I over 2 pi r, which some of us have seen presented as in the expression for the field made by a wire at a distance r from the wire, that being a long wire. And yeah, our pretty detailed analysis via Biot Savart bears that out. Okay? You will very shortly learn a much simpler way to do that. Analytically, a much simpler way. Okay, but this is a great exercise in a whole bunch of important analytical stuff to be able to do, like, evaluate a right-hand rule, talk about or evaluate a cross product via the right-hand rule, evaluate how we go from cross product to scalar product, doing a whole conversion of one set of variables to another. So lots of great analysis here. Okay? That's it, people. Congratulations.